In the last session, we studied resonance and we'll be doing some numericals on resonance in this session. So we have a circuit here in a series RLC circuit. A voltage source of 20 sine omega t, a resistance of 2 ohms, an inductance of 1 millihenry, and a capacitance of 0.4 microfarad. So we have to find out the resonant frequency. We have to find out omega 1, omega 2. We need to also find out the quality factor. We need to find out the bandwidth as well as the magnitude of current at omega naught, omega 1 and omega 2. So as far as omega naught is concerned, the resonant frequency is given by this formula 1 by under root of LC, which means 1 by under root of 1 millihenry, that is 10 to the power minus 3 into 0.4 microfarad, 10 to the power minus 6. So this is 50,000 radians per second. Then we have to find out omega 1 and omega 2. We can actually find out omega 1 and omega 2 using the formula for omega 1 and omega 2 that we derived in the last session, that is using these two formulas. Or we can also find out the value of omega 2 and omega 1 from the bandwidth of the system. Fine. So in order to do that, first of all, let us find out uh, Q for the system. The quality factor. The quality factor is given by omega naught L by R, or we can also say 1 by omega naught RC. This is 50,000 into L, that is 1 into 10 raised to the power minus 3 divided by R, that is 2. So this is 25. Fine. The bandwidth is given by omega naught by Q. That means 50,000 divided by 25, so that is 2000. So this is the bandwidth. Omega 1. Now to find out omega 1 and omega 2, we know that the bandwidth of the system is B is equal to omega 2 minus omega 1, represents the bandwidth. Uh, so if this represents our resonant frequency, this represents omega 1, this point represents omega 2. This whole here is equal to B, and since we are assuming that this is a symmetrical curve, so therefore omega 1 minus omega naught will be equal to B by 2. Fine. Omega naught minus omega 1 is equal to B divided by 2, which implies omega naught is given to us as 50,000 minus omega 1. We have to calculate B. We have already calculated out. It's 2000 divided by 2, which implies omega 1 is equal to 50,000 minus 1000, that is equal to 49,000 radians per second. Uh, Q is a quality factor is unitless, so this is actually 25 units. Bandwidth is it's simply the difference between two frequencies, so it is also having the units of frequency, that is radians per second. If omega 1 is equal to 49,000, we can substitute this here in this formula, b is equal to omega 2 minus omega 1, and find out omega 2. Or you can now directly also write, since the frequencies, since this is a symmetrical curve, omega 2 will be equal to 51,000 radians per second. It's 1000 on this side, 1000 on that side. So these parts are done. Now we have to find out the magnitude of current at omega naught and omega 1 by 2. So magnitude of current at omega naught is simply equal to V divided by R, where V is Vm divided by R. Vm is 20 divided by R, that is 2 ohms. So this is equal to 10 amperes. At omega 1 and omega 2, magnitude of current is equal to 0.707 Vm divided by R, or you can say Vm by root 2 R. This is 0.707 into 10, that is 7.017 amperes. In other words, we can simply say that the current magnitude at omega 1 and omega 2 will be 70.7%, 70.71% of the maximum value that is obtained at uh, the resonant frequency. Okay, so now we have a parallel resonant circuit. Has R equal to 100 kilo ohms, L equal to 20 millihenry, and C equal to 5 nanofarad. Calculate omega naught, omega 1, omega 2, Q, and V. So parallel resonant circuit has been a parallel RLC circuit with these values of R have been given to us. We have to calculate omega naught, omega 1, omega 2, Q, and B. That means we are actually not concerned with the source here at all. Omega naught is equal to 1 by under root of LC, 1 by under root of 20 millihenry into C, that is 5 nanofarad. The formula for omega naught is same for both series as well as parallel resonant circuits. So this is equal to 1 lakh, or you can say simply 100 kilo radians per second. So this is omega naught. Let us find out the quality factor first. As we know, for a parallel RLC circuit, the quality factor formula is R divided by omega naught L. So this is 1 by 1000 by 20, so that means 50. 50 units, it's dimensionless. The bandwidth is related to quality factor. Now this formula is same for both series as well as parallel circuits. Bandwidth is equal to omega naught divided by Q. Omega naught here being 100 K, quality factor being 50, so this is 2000 radians per second. Now we have the bandwidth, we know omega naught, so therefore we can say omega 1 is equal to 2000, it is 100k minus 1000 and 100k plus 1000, so that is actually 100k minus 1000, omega 2 will be 100k plus 1000. So this is simply omega 1 99 kiloradians per second. Omega 2 here is 101 kiloradians per second. Now here is your question. You have a circuit like this. So your question simply is here is find out omega naught, that is the resonant frequency for the circuit. Now this is not a simple parallel RLC circuit because with an L here we have a series resistance. So the formula omega naught equal to 1 by under root of LC is not actually valid here. So as I told you, for such systems we need to actually find out Z and put the imaginary part of this Z equal to 0, and from there whatever is the value of omega that we obtain will be the resonant frequency of the system. So let us find out Z, or we can directly find out admittance in this case. Admittance in this case is simply j omega c, that is 0.1 j and omega, fine, j omega c is 0.1 plus 1 by 10 ohms plus 1 divided by 2 plus j omega L, j omega j omega L is 2. So this is from this we actually need to find out the j terms, and you can either substitute impedance of Z equal to 0, or you can substitute impedance of admittance equal to 0. Both will give us the same result. So this is 0.1 plus 0.1 j omega. So by rationalization of this is plus 2 minus 2 j omega divided by 4 plus 4 omega square, which implies 0.1 plus 2 divided by 4 plus 4 omega square plus j. Internally we have 0.1 omega minus 2 omega divided by 4 plus 4 omega square. So this is our admittance. Fine. Now we have to actually substitute the imaginary part of this admittance equal to 0. Imaginary part of admittance equal to 0 means 0.1 omega minus 2 omega divided by 4 plus 4 omega square. When equated to 0, whatever the value of omega that we obtain from here will be the resonant frequency for this particular circuit. So this is 0.4 minus 2 omega, that is actually 0.4 omega square minus 1.6 equal to 0. Omega can now either be equal to 0 from here, which is very unlikely, and another value of omega that we can obtain is by equating 0.4 omega square minus 1.6 equal to 0. 0.4 omega square minus 1.6 equal to 0, which implies omega square is equal to 1.6 divided by 0.4. Omega square is equal to 4, which implies omega is equal to plus minus 2 radians per second plus negative frequency does not exist, so omega naught is equal to 2. Fine. So omega naught is equal to 2 radians per second for this particular case. Let's do one more numerical on this. Calculate the resonant frequency of this particular circuit. We have a voltage source fed circuit. This is 20 cos 80 volts. Fine, so A is actually not known to us. Omega naught, this is 12k, this is 45k, this is 1 microfarad, this is 60 millihenry. We need to find out all these values, omega naught, q, b, in this particular case. Fine. So this is actually fairly simple, this particular problem. We have a voltage source and we have a resistance in series with this voltage source. So we can apply source transformation here. So we'll get a current source in parallel with a resistance, and that will be in parallel with another resistance. So ultimately we'll be having one resistance, one capacitance, and one inductance here. Now what is the value of this current source here? This will be simply 20 cos 80. So this is actually the voltage. We have to convert it into current. So dividing by 12,000, that is the value of this resistance. And then this resistance value here is actually 12k in parallel with 45k now. This is 1 microfarad and this is 60 millihenry. So we have an RLC, simple parallel RLC circuit. Now we can use simply those formulas that we obtained for a simple RLC circuit. Omega naught is equal to 1 by under root of LC, so on and so forth. So you can do this problem from here. Let's look at another problem. Okay, we have a circuit here having a resistance of 1 ohm and inductance of 20 millihenry, a capacitance here of 9 microfarad, and a resistance of 0.1 ohms. So we have been asked to find out the resonant frequency of this particular case. So we can find out the impedance here. What is the impedance of this particular circuit? It is 1 ohm. We can find out the admittance and find the resonant frequency from there. Let's find out the impedance of this particular circuit. So we have 1 ohm that is in parallel with 20 millihenry inductor, that is actually an impedance of reactance of j omega L. So this is j omega L, that is 20 into 10 to the power minus 3, and that is in parallel with 0.1 plus 1 by j omega C. J omega C, C here is 9 into 10 to the power minus 6. So let us do first this portion of this. I think it's better to go with the admittance formula. The admittance of this is the conductance here is 1 divided by 1, that is 1. This will be 1 divided by j omega L, j omega C, and 1. So we have an admittance of y equal to 1 plus 1 by j omega L, that is 20 into 10 to the power minus 3 omega j, and plus 1 divided by 0.1, that is 10, the j omega C, that is 9 into 10 to the power minus 6 omega j. So this is equal to 11 minus, this is 1000 divided by 20, 50 by omega j. This 1 and 10 already 11, so this is 9 into 10 to the power minus 6 j omega, which implies 11 minus j 50 by omega minus plus 9 into 10 to the power minus 6 omega. So equating this imaginary part equal to 0, we have minus 50 by omega plus 9 into 10 raised to minus 6 omega equal to 0, which implies mm, minus 50 plus 9 into 10 raised to minus 6 omega square is equal to 0, which implies omega square is equal to 50 divided by 9 into 10 raised to minus 6. 50 divided by 9 into 10 raised to 6 root of the answer is 2357. So omega is equal to 2357.022 radians per second. Plus minus this resonant frequency cannot be negative, so we'll only be taking the positive value. So omega is equal to 2357, or you can say 2.357 kiloradians per second. So we have done some problems on resonance and both series as well as parallel RLC circuits. You can continue with you can do some more problems on your own, and in the next session we'll be now taking up the three-phase circuits. So that will be all for this session.